Welcome, ladies and gentlemen, to this video lecture. So now we will start looking at limits that tend to infinity. So before defining rigorously what this means, let's just take a look at an example. So let's say we have a function that is defined on all the real numbers except at plus or minus 3, and it maps into the real numbers, and it is defined as follows. F of x is 1 over x squared minus 9 for all x in the domain. So R without plus or minus 3. Okay, let's just think about what the graph of this function looks like. So the denominator is equal to 0 when x is equal to minus 3 or is equal to plus 3. And the value of the function is positive on to the right of 3 and negative to the left of 3 and positive again to the left of plus 3. And the graph looks something like this. And like so. So here, around 3, if you get close to 3 from this side, the function values, they get bigger and bigger and bigger. And if you get close to 3 from this side, then the function values get smaller and smaller and smaller. Or they become more negative with a very large absolute value. And similarly on here at minus 3. So let us just talk about how we can describe infinity. So what does it mean? So what does it mean that we say this function f tends to infinity as x tends to 3 from the right? It means that it doesn't matter how large a number we can take. Let's call it e. It doesn't matter how large we take. We should always be able to find a point here which maps to a function value which is larger than this number e. And it doesn't matter where we take this e. We can take it up here. We should be able to find a point here for which the function maps to a larger value there. So that is the idea of how we can describe infinity. Okay, let us write down the rigorous definition of what this means. Definition. Let f be some function defined on an open interval from a to b. Then the following means, so the limit as x tends to a from the right of f of x is equal to plus infinity. This means the following. And now pay close attention to how I write this. So this says for every positive number, capital E, there exists a delta greater than 0, so that if x is to the right of a but still within a delta distance, then f of x is bigger than e. So let us pause here. So what is different to the usual definition? So in the usual definition we used an epsilon for every positive epsilon. here we use a capital E. Why do we use a capital E? So this is to differentiate between, or let's say this is just a mnemonic device for remembering when things actually get interesting. So in this case we use capital E to denote a very large number. So any very large number, doesn't matter how big, we should be able to find a function value that is close to 3, that maps or has the graph above this large number. And we use epsilon. Epsilon is always a small number. So we use the capital E as just as a mnemonic device. So what this says is you take any large positive number, then there exists a delta, so that if you are close to A, within a delta distance of A, then the function takes on values that are strictly larger than this large number. Okay, let us talk about the next definition. So the limit as x tends to A from the right, f of x is equal to minus infinity. This means the following. This means for every negative number, capital E, so less than 0, there exists a delta greater than 0, so that if, actually let's write it this way, if x is to the right of A but within a delta distance of A, then f of x is smaller than E. So you can think about this. What does it mean? So for example, in our example we had that, or actually let's think about it this way. If you've got a function that tends to minus infinity when it gets close to 3, this says doesn't matter how large a negative number you take, you should always be able to find a delta, so that if you are within this interval of length delta, you should be able to find such an interval so that all the function values f of x lie below this line E, this horizontal line at E. And it doesn't matter what value you take for E, you can take it more and more negative and you should be able to find an interval here so that all the function values lie below that line. Okay, so that is the idea. Okay, and so of course you also have corresponding left definitions. So these are the limits as x tends to A from the right. As x tends to A from the right, then you also have corresponding left definitions. So also corresponding left definitions. Okay, and I will leave as an exercise for you to write down what the left definitions are. Exercise. Okay, then there is the following theorem. And what this theorem says is that it is always possible to convert a left limit into a right limit. So we are allowed to restrict ourselves to just considering right limits. So let f be defined on the open interval from a to b. Then the following are true. The following are true. So number 1, the limit as x tends to a from the right of f of x is equal to minus infinity if and only if the limit as x tends to a from the right of f of x of minus f of x rather is equal to plus infinity. So this says we are allowed to convert limits that tend to minus infinity to limits that tend to plus infinity. And how do we do that? We multiply the function by a minus. And this has the effect of flipping the graph of the function around the x-axis. So think of it this way. If you've got a function that tends to minus infinity, if you reflect around the x-axis, then you have a function that tends to plus infinity. Okay, so that is the first one. And we've got the limit. The second one is the limit as x tends to b from the left of f of x is equal to minus infinity if and only if and only if, not only if, only if the limit as x tends to b from the left of f of x minus f of x is equal to plus infinity. And all that this theorem says is same thing as we had in number 1 works for limits that tend to infinity on the left. So think of it this way: if we've got a number here, so if that is 3, and if the limit tends to minus infinity on the left, if you reflect around the x-axis, that is what this minus does. If you reflect around the x-axis, then the limit tends to plus infinity. So if this is f, this is of course minus f. Okay. And the next one looks a little bit strange. So let's take a look here. The limit as x tends to b from the left of f of x is equal to plus infinity. This holds true if and only if the limit as x tends to, no, actually I want to use a different symbol. T tends to a from the right of f of a plus b minus t is equal to plus infinity. Okay, so this one looks a little bit strange. Let's just talk a bit about what this means. So in fact, let's do it on 2 sets of axes. So let's say you've got an open interval here from 3 to 4. This says the function, if the function tends to plus infinity as x tends to 3 from the left, it's like we have over here, that is the same as saying if you reflect this function around the halfway point here at 3.5 or 3.5. So if you reflect the function around this symmetry axis, then of course the function is reflected, and then the limit as you tend to 4 from the right tends to infinity. So this is what this transformation does. It flips this interval around the axis, the symmetry axis, or around the center of the interval. Let's just think about how this works. So if you've got 3 and 4, and 3 and 4 over here, and think about if this is t, and if our transformation sends t to 3 plus 4, no, what was it? 3 plus 4 minus t. 3 plus 4 minus t. If t is equal to 3, we see here, then 3 plus 4 minus 3, the 3's cancel and we're sent to 4 here. So we see over there values close to 3 are sent to values close to 4 over there. If we are at 3.5, then you, if you work out this expression, you will see that is sent exactly to 3.5, and it flips all these points around this axis at 3.5. And if you're close to 4, then of course the 4 and the minus 4 will cancel here, and you're left with the 3. So this is how this transformation works. And all that this says is, all that this number 3 says is, if you flip the graph around this symmetry axis using this transformation, then the left limit transforms into a right limit. Okay, and in the next video we will discuss an example. I will see you in the next one.